Hello student, welcome to our physics discussion, that is physics in a smart way. In our last video that involves the discussion of specificates where you have been asked to take up some formulas without logic of course, because I need to promise you that logic will appear in due time and in a short time that too. So our last the issue was the change of internal energy will be equal to number of moles of the gas into specific heat at constant volume into change of temperature. And as I remember, I did remind you that this is an universal formula. Sometimes student gets confused in the way that they may think that CP means specific heat at constant volume. The teacher has told me that a gas can have many different types of specific heats, practically infinite or millions of sources, specific heats. So out of them, CP is specific heat at constant volume. So maybe this formula would work for a constant volume process. No, we have to look through CP into the thing where when CP is replaced by the issues like degree of freedom and all those things, which are process independent. So this formula is an universal formula. This formula is an universal formula, though the formula is derived under constant volume condition, but still then the formula has got universal application. So that was the last statement. Okay. Let me remove it and let us go into the things. When we say things, now the time has come to go to individual processes. The first process that we got in our hand, the simple process, is a constant volume process. Constant volume, normally it is mentioned in our books as isochoric. Sorry. Process. A constant volume process or isochoric process where volume is constant. Usually, whenever you take a process and you study it, we know we are studying considering our thermodynamic parameters. And those parameters already we have discussed. One is pressure, second is volume, and third is temperature. So when you discuss the process on the basis of the so-called thermodynamic parameters, there are usually 5 issues or 5 points or 5 minders, 5 important aspects which are required to be considered. And the first one is state equation. State equation. You might be wondering what is this. State equation usually means using the thermodynamic parameters, pressure, volume, and temperature. Do you got any formula which is valid for this heading or constant volume process? My point is that a student can immediately point out that yes, we got a formula which is a universal gas equation, PV equal to nRT. But you know, in universal gas equation, we got 3 variables, maybe pressure, volume, and temperature. But if you are having a 3 variable case, if unless you put down the value of 3 variable, 2 variable, then third one is not going to come out. Third one we are not going to find out. So usually when we say state equation, we consider a XY type equation where the value of X is put down and Y will be coming out. And the value of Y is to be given, and the equation will be given with the value of x, that type of thing. And already you know the universal gas equation, that is PV equal to nRT. We know that is valid, that is a state equation for every process. Every process you may think of. So thereby, whenever we got a process must be having taking the pressure and volume temperature, but there are three quantities, so taking two out of them, because we need an XY type equation, so either pressure volume or volume temperature or pressure temperature. So thereby we need to get a formula. And here our universal gas equation will be helping us also. Let us find how. We know the heading says constant volume process. So when the heading says constant volume, you know volume is constant. Once somebody mentions that volume is constant, volume is no longer a variable. So then out of pressure, volume and temperature, because volume is constant, volume is no longer a variable, so only two variables are pressure and temperature. So our state equation, obviously logic says, must be consisting of these two variables. One is pressure and other is temperature. Okay, so what sort of equation we're having? If still the idea doesn't hit us, then we may take the help of universal gas equation. We know which is a branded state equation for any process. PV equal to nRT, where N is number of moles and universal gas constant. Once you select a gas, you cannot change the number of moles. N is a constant. We know volume is a constant, number of mole is a constant, and R is a constant. So thereby we know pressure will be equal to a constant into temperature, where the constant will be equal to Nr by V, or pressure is directly proportional to temperature, or a student can say P by T is constant. Pressure by temperature is constant. Are you getting me or not? I think I am clear because these are school level mathematics. So that is the state equation. Here the state equation is pressure by temperature is constant, or P equal to KT, where K equal to Nr by V. So thereby if you write down the state equation, so that will be P by T equal to constant. Maybe C or K or something like that. P by T equal to, or maybe we may write it as constant, P by T equal to constant. Okay, let me remove those things which we have utilized already and no more delete. So first step is complete, that is state equation. Second step is the formula of work done. So far as thermodynamic work is concerned, we know thermodynamic work that has got a formula in the form P delta V, or that is integration of PdV. It has been already discussed, but P delta V formula can be used only for a constant pressure process. Here our case is not so. So our formula will be integration of PdV. But whatever it may be, we do know, because we know volume is constant. So change of volume you may write in the form of delta V or dV must be equal to 0, because you are not permitted at all to change the volume. So because delta V or dV equal to 0, because the gas cannot change the volume, you may be having a force acting on a body. The force may be, let us say, several million newtons. But if the body is having no, so to say, displacement, then work equal to always 0. So thermodynamic work, because delta V and dV equal to 0, so that is 0. Number three, or the third step that usually you get, or the third point that you usually get, that is the first law. That is a first law. First law means first law of thermodynamics, as it has been discussed before, I am not writing thermodynamics, I am writing thermo first. Or let us say we write it complete. Thermodynamics, which has been discussed already. We know the first law of thermodynamics as it says Q equal to, in macroscopic form, Q equal to, don't try to write in dq, du, all those things. They are not required every time. So Q equal to delta U plus W. Or some books may be writing delta Q equal to delta U plus W. Okay. Okay. In whatever form you may write, no problem. No problem. We know basically this means Q is the heat given to the gas. And here right hand side, how the gas utilizes that out of the heat that you have given to the gas may want to try to keep something in it, and once gas tries to keep a part of the energy you have given to it inside it, we know its internal energy must increase. And second, the gas may be doing some work in that issue. I have shown you how the gas expands and compresses spring and how work is done, and higher work how the gas is sending energy outside. But in this case, we know in any constant volume process, our work is zero. So when our work is zero, you can clearly see the gas behaves in a most miserly way, selfish way. Selfish way. In my mother tongue, we say that is kampi, that is selfish, most miserly way. That means whatever heat you give to the gas, the total amount of heat, the gas will be keeping it within itself. It doesn't want to do some work. It doesn't want to send energy outside. So the role of the gas in a most miserly way. Number four, the fourth idea is specific heat. Specific heat. Specific heat, if you say, already it has been discussed, a gas has got many different specific heat under different conditions. It shows different type of specific heat, but the basic formula of specific heat, C equal to Q by N del T. Heat absorbed by the number of mole per 1 Kelvin change in temperature. But because it's a constant volume process, so here the specific heat is a branded one, that is CV. CV. The specific heat for a constant volume process is known as CV. But as you can see, once we know you are in a constant volume process, we know Q equal to delta U. But if I am replacing Q by delta U, then Q can be replaced as delta U by your N del T. And now cross multiplying it, we got what we got? We got delta U equal to NCV del T. We have arrived again at the universal formula delta U equal to NCV del T. I have told you before, the formula will be derived, will be coming across the formula, so don't worry. But mind it, again I am giving you the second binder. Though the formula is derived for a constant volume process, that is not valid only for constant volume, that's a universal formula. That has got some universal symptoms. So the first point was, I am repeating again, taking you back again. The first point was the first point was the state equation. The second point was work done. The work done. I have missed something. You just write in once work done, then comma W. So you have to write like this: work done, or work, comma W equal to this much. That is the form of the first law of thermodynamics, which is based on energy balance for this case or for this process. And the fourth is the specific heat. The fifth and the last one will be, let me clear up some space, will be graphs. In this case, because most of the quantities, pressure, temperature, and all those things, they are not visible. So let me clear up some space, graphs. But the moment we got graphs, we know our graphs are two-dimensional. Graphs are two-dimensional. When you say two-dimensional, and usually they involve the thermodynamic parameter. One is pressure, second is volume, third is temperature. But there are three variables. So considering any two of them, we know there are three quantities: pressure, volume, temperature. We have to select two. So basically, that is combination of two objects out of three objects. That is a mathematical issue. That is 3C2, or maybe now we are writing 3C2 like this. That is equal to 3 waves. Very easily, we may not think of combination. Very easily, you can find out that is, it can be either pressure temperature or volume temperature, or maybe that is pressure volume graph. So thereby, if we consider the graphs like this, but first graph, the graph number 1, I got volume on x-axis and pressure on y-axis. Second graph, I got volume on x-axis. You may take volume on y-axis also, no problem. And temperature y-axis. Third graph, we got temperature on x-axis and pressure on y-axis. That is second, and this is third. Okay, constant volume process. So if we are permitted to, for the first graph, we know because volume is constant, so pressure can be increasing or decreasing, doesn't matter. But the graph is to be like this, the volume is constant. Similarly, the second graph, we know the process is the constant volume process. So thereby, the graph will be like this. Your temperature may be increasing or decreasing for a particular process, but because the process is branded as constant volume process, so thereby we know that will be a constant volume process where x-axis is constant because we have taken volume. The third graph, P by T is constant. But once we say P by T is constant, we know P by T is constant. That was our state equation. P by T is constant. So if I take that constant as M, and pressure I have taken on y-axis, temperature I have taken on x-axis, that becomes y by x equal to m. So y equal to mx, that becomes a straight line passing through origin. So thereby, we know that becomes a straight line passing through origin. A straight line passing through origin, and the straight line will be like this, unlike the first and second graphs. Sometimes you may be requiring the slope of the line. So if you consider the slope of the line, we know the slope also can be found out. Slope m, that is equal to tan theta, that can be found out very easily. We know P by T is constant, but we know PV equal to nRT, that is universal gas equation, that is mother of our old friend. So if we separate out P by T, so here it says that P by T will be equal to NR by V, NR by V, and here the slope is tan theta. On y-axis we get pressure, on x-axis we get temperature. So here slope equal to P by T, but writing P by T doesn't help in any cause because P is variable, T is variable. So that is NR by, we got our old friend helping us. The first law, NR by V, that is the slope. Okay, so thank you. That is the idea on a constant volume process. Those 5 points should be every time considered. We go to any process. So today, I think it's enough. We'll be taking the next process, that is constant pressure process, next time.